Today we're going to give you some mathematical background that will help you deal with different thermodynamic quantities. So we're going to be looking at functions that depend on multiple variables. So to do that we need to deal with multivariable calculus. So to start off with, we're just going to look at derivatives for functions of a single variable. So here I have a function y of x. I know that I can take a derivative of that function. Say I take a derivative of a function at that point. We know the derivative is just going to be the slope at that point. So we can write that slope as dy dx. And that's our derivative for a function of one variable. Now it's going to get a little bit more complicated if I have to consider functions of two variables. Let's see how that's going to work. When we take a derivative, we're looking at the rate of change of some variable with respect to another variable. But what happens if your function depends on multiple different variables? Suppose you want to change a couple of different variables at the same time. Well, that gets a bit more complicated. Let's take a simple example. Say we have a function z that depends on both x and y, and z takes the shape of this kind of mountain shape when I plot it as a function of x and y. And suppose I asked you to measure the slope at a point. Say I want you to measure the slope at this point right here. Well, it clearly depends on which direction you're measuring. If you're going around the mountain, color code here a little bit, if you're going around the mountain this way, z is almost flat, it's pretty horizontal, so you're not going to have much of a slope. However, if you were looking along this path, making x bigger, you do have an appreciable slope. You're going straight down the mountain along that path. So we want a way to account for that. And one way of doing that is looking at the total differential, something called the total differential. So what I'm going to do is I'm going to look for a small change dz. So I am going to make a change dz. By changing two variables, I'm going to make a small change in the y, and I'm going to make a small change in the x direction. And we're going to see how z changes as we do that. Well, the first thing I want to do is, let's say we want to change x first. So let's change x while holding y constant. So we're going to change x, see what happens to z. Well, that's a particular type of derivative that we're taking here. We're holding one constant. We're holding y constant while we look at the change in z due to a change in x. When we do that, that's called a partial derivative. It's going to give me the slope along the x direction. The way we write that is dz dx. Notice I have a funny looking curly d there. That's the partial derivative. dz dx. And I want to denote that I am holding y constant. So I'll write that as dz dx at constant y. The subscript y tells me that we're holding y constant. And much like we would write a total derivative, if I just multiply this by dx, my small change in x, I get my dz back. So I look at the slope of z along the x direction, multiply by how much I've changed x by, that small amount dx, that tells me how much I've changed dz by. Or more explicitly, it would tell me how much I've changed z by if I also account for the changes in the y direction. So let's see what happens when we change things in the y direction. Well, it's going to be pretty much the same thing. I'm going to look at how z changes in the y direction. So I'm going to look at the slope of the z function in the y direction, but keeping x constant. So we'll say dz dy constant x. And I want to take this slope and multiply it by how far we moved in that y direction. So we'll say that's dz dy dy. So just a couple of notes on notation here. This dz is my total differential. We call that our total differential. So that's how much z has changed by making a change in x and y. Differential. These, the dz dx at constant y and the dz dy at constant x, these are partial derivatives. It's a partial derivative because I'm only taking a derivative of part of the function. Right? The dz dx keeps y constant. It doesn't take any derivative with respect to y. So if I wanted to take the full derivative, I would have to take partial of z with respect to x. But then I'd also have to take the derivative of y with respect to x. We don't want to do that, not for this type of problem. So we're just going to take the derivative of z with respect to x, but we're just going to treat y like it's a constant. This is how we're going to set up our total derivatives, or our total differentials. These are going to be very important in thermodynamics. Just as we can take derivatives, we can also take second and higher order derivatives. So a derivative gives you the slope. Second derivative gives you the curvature. So for example, if I'm plotting y as a function of x, and I take d squared y dx squared, this plot should give me a positive second derivative because it's got the smiley face going on. This plot should give me a negative second derivative. It's just a matter of whether the plot is concave up or concave down. That tells you what the curvature is, it tells you what the second derivative is. We can do a similar thing in using multivariable calculus. And it works pretty much the same way. We can take a, let me stick with my original variables here. So let me take a second partial derivative of z with respect to x. I could also take a partial derivative of z with respect to y. You can do that twice, we get the second derivative. We could do mixed derivatives here. So instead of d squared z dx squared or d squared z dy squared, we could instead do d squared z dx d squared z dy. What does that mean? Well, what it means is that first I take a partial derivative of z with respect to x, or with respect to y, keeping x constant. Then I take another partial derivative of this partial derivative, except now I take it with respect to x instead of with respect to y. This time I hold y constant. So I take the partial derivative with respect to x, or excuse me, take the partial derivative with respect to y holding x constant. Then I take the partial derivative with respect to x holding y constant. Now you might wonder whether or not this depends on the order that I take the derivatives. So let's say I do it in reverse order. So instead of taking dz dy holding x constant, suppose I took the partial of z with respect to x holding y constant. Now I'm free to do the other derivative. I've already done d by dx. Now let's do d by dy. Holding x constant. It should be true if you have what's known as a state function that these two things are going to be equal. So let me explain what I mean by that. And I think the best way to see that is through an example. So let's take an example from thermodynamics. Let's use the ideal gas law. So the ideal gas law says that PV equals nKT. I'm going to write pressure as a function of the volume and the temperature. So P, as a function of the volume and the temperature, is going to equal, well, pressure times volume is nKT. Therefore, pressure has got to equal nKT divided by the volume. Okay. All I'm doing now is I am replacing my Z with pressure, because it's pressure as a function of volume and temperature. So instead of Z, I have pressure. Instead of X, I have volume. Instead of X, I have volume. Which means I've got to change my X over here. So pressure depends on volume. And instead of Y, we'll have temperature. All we're doing is just changing the letters around. But now, when I change the letters around, it means something physical. If I have a gas, and I want to know the pressure of that gas, it will depend on how much I have compressed my container, so it'll depend on the volume of the container. And it will depend on how much I've heated that container up. So it must depend on the temperature of the container. If it's an ideal gas, all I'm doing is solving my ideal gas equation for pressure, and then we can say that the pressure is a function of the volume and the temperature. Now I could have done this another way. I could have said what's the volume as a function of the pressure and the temperature, or what's the temperature as a function of the pressure and the volume. It doesn't really matter which variables I use, it's just using algebra to solve for the different variables. But let's actually take our mixed second order derivative and see if those two things are equal like I said. So first thing I want to do, let's take dP dV, holding temperature constant. So I look at that. That means K is a constant, N is a constant. I'm going to treat temperature as a constant, even though it might not be. And I'm going to take a derivative with respect to V. All right. Well, NK and T are constant, so they're just going along for the ride. They're not going to change. I've got a 1 over V. The derivative of 1 over V, just using the one down rule, is going to be 1 over V squared times -1. Okay, so that's dP dV at constant T. Let's do another derivative. Let's now take d by dt of this thing. So we're going to take d by dt at constant V of dP dV at constant T. So now I'm just doing another derivative, this time with respect to temperature. And you will see, taking a derivative of this guy with respect to temperature, well, now I'm keeping V constant, so I don't have to worry about that. So that means that the minus nk over V squared, those are all constants. The only thing that's not a constant is the temperature. I take a derivative with respect to that temperature. It goes away, I'm just left with this. Now my claim is that it does not matter which order you take the derivatives of if you are working with a state function. Again, I'll talk about what I mean by a state function momentarily. So let's try doing that. Just erase this. Okay, so here is my function. I took a derivative with respect to volume first, then I took a derivative with respect to temperature. Let's do that in the reverse order now. Let's take dP dt, the derivative with respect to temperature, instead of the volume. We're going to do that one first. We're going to hold the volume constant. So that means the derivative of P with respect to temperature, holding the volume constant, well, NK and V are all constants. So they're just going along for the ride. Take a derivative with respect to t. The derivative of t with respect to t is just 1, so I just get nk over v. Now, let's take this function. We're going to do that mixed second order derivative, which means I took a derivative with respect to t first, then I'm going to take a derivative with respect to v. So now, I'm going to take a derivative with respect to v, holding t constant, and I'm going to take a derivative of this guy, dp dt, constant v. All we're doing is taking derivatives of one variable holding the other variable constant. Well now, let's see. I'm taking a derivative of this with respect to v. N, k, those are constants, so they're just going along for the ride. The v is not a constant. I'm taking a derivative of 1 over v. So I should get, the derivative of 1 over v is v squared times negative 1, so that should be v squared times negative 1. Lo and behold, you see, we get the same thing no matter which order I take those partial derivatives in. So if I take the partial derivative with respect to temperature first, holding v constant, doesn't matter. I could take the derivative of that first, or I could take the derivative of the volume constant, or the volume first, holding temperature constant. You will get the same thing once you take the second derivative. So we took a derivative with respect to t, then we took a derivative with respect to v. We get an answer. It's the same thing if you go in the reverse order. Take the derivative with respect to v, then take a derivative with respect to t. This should always be true if we're dealing with a state function. So, state functions satisfy this nice mathematical relationship where the mixed second-order partial derivatives are the same no matter which way I take them. So whether I take dx first and then dy, or I take d by dy first and then d by dx, doesn't matter, they should be the same. I told you those were that was a property of state functions. What do I mean by state functions? I think the best way to see that is through an example. So here's an ideal gas. It is going to have several state functions. State functions just tell me about what state the system is currently in. So for example, my ideal gas has some temperature associated with it. If I know the temperature, I know something about the state of the system. Therefore, temperature is a state function. If I know the energy of the gas, the total kinetic energy of my ideal gas, that tells me something about what state it's currently in. It has a certain volume. Volume is a state function. It has a certain pressure. Pressure is a state function. All of these tell me about the state that the gas is in. Later on, we'll talk a bit more about the entropy of that gas. It has a certain entropy. Entropy is going to be a state function. I could also, if I wanted to be extra explicit, I could say the number of particles is also a state function. It tells me something about the state of the gas. I could have added more or less particles, but I know it has n particles, so I know something about the state of the gas. What are some things that are not state functions? It looks like I'm listing everything here. Well, something that's not a state function, say I look at the work that I did on the gas. Well, work doesn't tell me anything about how much energy the gas has, what temperature it's currently at. It tells me how much the energy has changed, but it doesn't tell me what state it's actually in. It doesn't tell me how much energy I actually have. It just tells me about some change that happened. Similarly, heat. The heat that I add is not a state function. It doesn't tell me anything about the current state the system is. The current state the system is in. All it does is tell me how that system has changed in the past. It tells me, well, I had some energy before, then I heated it up, I've got more energy now. But it doesn't tell me exactly how much energy I have now. So these are not state functions. These are examples of state functions. Now, we can use that mathematical property that we talked about, relating the order of the partial derivatives, the two different orders that we can use, and setting them equal to each other. We can use that to derive very useful properties. We can use that to derive equations of state, much like the ideal gas law for different materials. When I have a function that is a state function, we refer to its differential as an exact differential. Now, exact differentials have very nice mathematical properties. So let's try rewriting this exact differential in this way. I'm still going to keep my dx, but I want to write the partial derivative of z with respect to x, keeping y constant. I'm going to write that as just some function. So I'm going to write it as some function of x and y. Call it m of x and y. So all I've done is I have taken this and I have written it as that. Similarly, I can take dz dy, oops, d to dy here. I can take dz dy at constant x, and I will write that as some other function. I'll call that n as a function of x and y, dy. So again, all I've done, I'm just giving it a nickname. I've taken the partial derivative of z with respect to y at constant x, and renamed that as some function n, which depends on x and y. And I can do this because I know my original function z was just a function of x and y. Therefore, the partial derivative of z with respect to x, keeping y constant, has to just be a function of x and y. Same thing with the partial derivative of z with respect to y. Keeping x constant, it's just going to be some function of x and y. So I do that. Now, we've just said that the derivatives, the partial derivatives, if I take a d by dx and then a d by dy, doesn't matter which order I do that in. Therefore, it must be true that dm dx, or excuse me, dm dy, so I've taken a derivative with respect to x to get m. Now if I take a partial derivative with respect to y, holding x constant, that must be equal to dn dx at constant y, because to get n, I took a partial derivative with respect to y, then I take a partial derivative with respect to x. So I've taken my two partial derivatives, I've just flipped the order of them. First I took a dx, then I took a dy, then I took, in this case I took a dy, then I took a d by dx. This has got to be equal to each other if we have a state function. So this is a nice relationship to pay attention to. These are known as Maxwell relations. Suppose I have a gas. A container with some piston in it. And I want to do some thermodynamics on this gas. I want to understand the properties of the gas. Maybe it's not an ideal gas. It's some exotic gas that has interesting properties. Well, suppose I want to know how this exotic gas, how its volume changes as we change the pressure and the temperature. Maybe it has some very weird properties, very interesting properties that we could sell to somebody and make millions of dollars. Well, chances are I am not going to be able to just guess what this function is. Volume is a function of pressure and temperature. I don't know. We need to measure that in some way. To do that, we can go back to our exact differential. We can say dV equals. Well, I automatically know how to write this down. Volume is a state function. I know it's got to be some function dp plus some function dt. Let's just write it down. Let's write down what we know has to be true mathematically. It's got to be true that this is dv dp, constant t, dp, plus dV dt, constant P dt. There's nothing I did involving any physics here, that's just a mathematical relationship. All right, well, how does this help me find out what the volume is as a function of the pressure and the temperature? Here's where it gets very, very nice. How does my volume change as a function of the temperature? Well, we've talked about that. We've talked about how volumes of things change as you change the temperature. We said as you heat things up, they start to expand. Right? We related how the volume changed to a thermal expansion coefficient. Right? That's something we can measure. So I can measure my thermal expansion coefficient and find what that partial derivative is. All it is telling me how the volume changes as I change the temperature. It's exactly what a thermal expansion coefficient does. What about the volume change as a function of the pressure? Well, it turns out that's also something you can measure. Here we're talking about how much our gas can be compressed, how compressible it is. And we're doing it at constant temperature. Constant temperature means, what we call it, constant temperature, is just isothermal. And we're looking at how easy it is to compress the gas. So this is known as isothermal compressibility. So by measuring how our gas responds to external stimuli, so how it responds to changes in pressure and temperature, I can measure these response functions, these functions that tell me how my gas responds to different external stimuli. And once I know those, I should be able to measure, or should be able to calculate, what the volume as a function of the pressure and temperature is. I'd like to make a brief aside here, because I realize we haven't yet gotten a chance to talk about the volume expansion coefficient, or the isothermal compressibility. So we had just finished talking about how we can measure these functions. And in general, these partial derivatives are going to be different response functions that we can measure based on how the system responds to changes in external stimuli. So for example, we change the pressure, we look what happens. We change the temperature, we look what happens. Okay? So if we change the pressure, keeping the temperature constant, we could compress or expand the material. When that happens, we get the isothermal compressibility. Isothermal, again, because the temperature is constant, compressibility because we're compressing the gas. So it's not equal to just the partial derivative. There's a little bit more, which is why I wanted to go into this in more depth. But it's just dV dP at constant T. That's your partial derivative. But then you divide by the volume just to scale the compressibility. There's also a negative sign in front. That's just because if you add more pressure, you expect the volume to get smaller. We just want to account for the fact that it's getting smaller, which would be a negative number. In contrast, say we go back over here. We look at our volume change as we change the temperature while keeping the pressure constant. That's known as thermal expansion. Before, we focused primarily on linear thermal expansion, so how does the length change? Now we're looking at how the volume changes, which is basically the same thing, except instead of the length we have a volume, so it's dV dt. We're using a partial derivative now. We're being explicit that we're keeping the pressure constant. Now we could have kept other things constant. We could have kept the total energy constant, or we could have kept other thermodynamic variables, other state functions constant. We're keeping the pressure constant, taking 1 over V. The long story, the short version of this, or the more general version of this, is that I can replace any of these V, T, and P variables. I can switch them around and get a different response function. I could replace them with a V, a P, a T. I could replace it with the energy. I could replace it with the entropy. I could even replace it with the number of particles. all we're doing is just playing around with different mathematical variables, and we'll get some thermodynamic response function. These two happen to be particularly nice because they're things that we have already had experience calculating, and they're things that are readily easy to measure. Suppose we want to find the state function for the volume of an ideal gas. Let's suppose we don't know the ideal gas volume. How can we figure out what the volume is as a function of temperature and pressure using exact differentials? Well, we can measure, and people have measured, the rate of change of the volume with respect to the temperature at constant pressure. So this is going to be my thermal expansion coefficient, or related to my thermal expansion coefficient, excuse me. And we can write this as Nk over P. People find, they measure this, they find it's equal to Nk over P. We also know how the volume changes as you change the pressure if you keep the temperature constant. And what you find is that you get something that looks like this, nkt over p squared and a negative sign. How can I use this information to figure out what the volume is as a function of temperature and pressure? All I have are the partial derivatives. It turns out this is enough information to solve the problem. All I have to do is write down my exact differential. I have dV equals dV dP, should be a partial derivative there, dV dP at constant T dP, plus dV dt at constant P dt. Now that must be true. It's mathematically true because V is a state function. I can always write that down for anything that's a state function. I can write it as a function of two variables in this exact differential form. But not only can I write down the partial derivatives, I actually know what they are because people have measured them. So let's see how that affects things here. So let's just plug in for dV dP at constant T. dV dP at constant T is minus nkt divided by p squared. Still have a dP over here. And I can also plug in for dV dt. That'll be plus. Let me give myself a little bit more room here. Don't want to run out of space too quickly. Minus nkt over p squared dP plus dV dt at constant p. I've got my dV dt at constant p over here. That's just nk over p dt. So the differential volume should be equal to that. Now how did I get my differential volume? Well, I got it by taking partial derivatives of v and t with respect to p. Except I never actually did that because I didn't know what that was. But if I did know what that was, if I did know v is a function of t and p, that's what I want to find. If I did know what it was, I would just get this by taking partial derivatives of it. So if I want to go the other way and take the partial derivatives and use them to find v as a function of t and p, I've got to undo those partial derivatives. How do I undo a derivative? You take an integral. So what we'll do, I'm going to erase this to give myself more room. Now this is where it gets a little bit tricky. So I started to get these partial derivatives. I took dV dP first and then dV dt. But I can't just integrate both of these and then add them together, because then I'm going to get twice as much as my state function really is. Why do I get twice as much? Well, if I integrate this side, I should get a v. If I integrate that side, I should get a v. So I'm going to get two v's out at the end. So I don't really want to do that. But I do actually need to do both integrals because this is only going to find all of the p's. When I do the p integral, if there's part of the function that just depends on the temperature, it's not going to show up when I do the p integral. When I do the integration of the t variable, if there's any function that depends just on p, that's not going to show up. So let's do two integrals. Let's do this integral, and let's do this integral. And then we'll compare and see if we can figure out what our v as a function of t and p has to be. Okay, first, let's do this integral. So we're going to integrate. Actually, let's just write this out. V. Let me actually give myself a bit more room here. V as a function of t and p equals the integral of this thing. Integral minus nkt over p squared dp. Well, that's a pretty easy integral to do. nkt are just constants here. We're treating the t as a constant. So I can pull those out of the integral. I am left with minus nkt integral dp over p squared. The integral of 1 over p squared is just 1 over p with a negative sign. So my negative signs will cancel. This will give me nkt over p. Now I have to be careful here. This is where partial derivatives are different than normal derivatives. So normally you do an integral and you say plus a constant. But the constant here depends on the temperature. Right? Remember we said temperature, we're treating that as a constant when I take my partial derivative. So plus a constant, but that constant really could depend on the temperature. So my v is this, plus some constant that could depend on the temperature. Right. So I've done this integral. Now let's do the temperature integral. So I've got to erase a little bit here. Let's erase some of this, give myself some room. I'll leave that there because I'm going to want that in just a second. So now we're going to integrate this thing with respect to temperature to find what v is a function of p and t is. So my volume, again, is a function of pressure and temperature. I really should have kept my order here. Sorry about that. Volume is a function of pressure and temperature equals the integral of this thing, nk over p dt. Now that I've written that out, I can erase that. Okay. Well, that's a particularly easy integral to do. N is a constant, k is a constant. We're treating p as a constant because when we took the partial derivative, we treated it as a constant. So I'm just going to pull all of those guys out. That's going to be nk over p times the integral of dt. What's the integral of dt? That's just t plus a constant. So v is going to equal nkt over p plus a constant, but now I have a different constant, right? This was a different interval. I'll call that constant 1. This is constant 2. And just like t was a constant in that integral, p was a constant in this integral. So I have to pay attention to the fact that the constant could depend on p. So let's look at what we got. Okay, so here's my other integral. I think I had we're still color coding, I think I outlined that in green before. Now if this is a state function, these two integrals should give me the same thing. We have v equals nkt over p V equals nkt over P. We're good so far. That's just our ideal gas law. What about our constants? Well, maybe there's something that depends on temperature. But I've already got my temperature dependent showing up in my T integral. And I don't have any extra T terms. So I know that this has just got to be 0. If it was not 0, there would be plus something times T, or some other plus a something with a T in it over here. And I don't have that. And similarly, I know that this constant has got to be 0 as well, because if it was not 0, I would have a plus of something with a P over here when I did this integral.